Hello everyone and welcome to yet another recreation programming session with Mr. Zozin. So this isn't a fly session, so there will be no chat or anything. I have this binary file, 4 megabytes. And I acquired this binary file by essentially running byte pair encoding algorithm on 33 megabytes of the logs of our Discord server. So for those who don't remember or doesn't know, byte pair encoding is an algorithm that basically counts the frequency of each individual pair of the character in the text and replaces the most frequent pair with an unused character, or in our case, code. Right, so, and then it repeats the process until there's no repeating pairs, and there's this table that shows the correspondence between a particular code or character and a pair of other codes and characters. Right, so this particular file is actually an array of 32-bit integers, in fact an array of pairs of 32-bit integers. So exact schema is roughly something like this, right? So here is a single pair, right, and you have left and right code, and basically the entire file is an array of these pairs. So what's interesting about this particular structure that you get out of compressing this text in this way is that it kind of implicitly defines a grammar of the text, right? Because it tells you that within the text, after the character A, usually, quite often, frequently comes the character B, right? Because we're placing the most frequent pairs in here. So, and because of that, you can actually, maybe based on that grammar, generate more text. It's probably going to be gibberish, right? But it's going to be kind of like a plausible text, sort of like in the style of Markov chains, right? So, and what's funny is that these kind of tokenizers are used within the large language models, right, to split the text into, tokens that are reasonable to process, right? Because the large language models don't operate on individual characters because it's too much resources. You need to group these characters into chunks that are easier to process, and byte pair encoding is used to identify these kind of chunks that are easier to feed into large language models. So what's funny, this particular thing kind of indicates that large language models and language models in general, they store knowledge and data not only within the weights of their models, right, so neural networks, transformers and stuff like that, but also they store a little bit of knowledge within their tokenizer. Right, so just a tiny bit, not much, but just a tiny bit. And since I acquired this pretty big table, relatively big table, I think the time has come to try to maybe generate more gibberish out of this implicit grammar that we acquired from the logs of our Discord server. Right, and that's basically what I wanted to do in today's session. So let's actually introduce a new tool into our tool suite that we have in here. Let's call it, I think I'm going to start with the node.c. Let's call it something like bpe gen, right? So, and let's create a file here, bpe gen.c. So I'm going to include bpe.h, which contains basically shareable code between all of the utilities that we use to generate all of that stuff. And in here, we will probably need a function that loads the pairs. There we go. So that's the function we need in here. So the first thing we'll need is file path to the BPE file, right? So byte pair encoding file. And we can acquire it through the command line arguments. Recently, I actually rediscovered a library of mine called flag.h, right? So it's basically an implementation of an idea from Go, right? Go, in its standard library, comes with an interesting package called flag, which enables you to parse command line arguments, and I think it's rather convenient. I really like this idea, and some time ago, I implemented it in C, right? So I'm going to actually put it in the description. I think it's a good idea to share it with everybody. Right, and then at some point I kind of forgot about this library, and then I rediscovered it again, right? So it's actually kind of cool library. So people still send pull requests. It's pretty old. So yeah, and I started using it everywhere, so it's pretty cool. So let me, on top of that, also include flag.h, and it's a header-only library. That means I have to do flag implementation like this. So, and what we'll need, so far we'll probably need one flag, which is the path to the file. So the way you do that, you have to create a flag with the type that you need. In our case, we need a string So we're gonna do it like that. I'm gonna call the flag something like BPE. Emacs didn't remove the selection. So the default value is going to be null because by default it's not set, and we're going to have some sort of a description in here. Path to BPE file, right? Sounds reasonable. And it returns a variable that points to a pointer to the character. So essentially what it does, it points to a string, right? So, and another thing that we'll need in here is the help flag that will print all of the available options and stuff like that. So for that we have flag boolean. Right, let's actually copy paste it in here. So here's the flag boolean. So I'm going to call it literally help. By default is not going to be set, right? So you set it explicitly. So it's false, and we're going to do print this help message, right? Because this particular description is going to be visible within the help message, right? So it's going to be called help. So after we defined all of the necessary flags, and we can always add more, we are going to parse all of the flags from the command line arguments like so. So, and if we didn't manage to parse, maybe some sort of syntactical error has occurred, it will return Boolean, it will return false, and we'll have to print usage and an error. So let's actually create maybe a separate function for printing usage. This is something that I like to do, because I usually have to print the usage several times. So what's going to be the usage in here? So what's funny, I don't even need to know the name of the program, because the name of the program from the command line arguments has been consumed by flag parse, and I think you can even extract it. So there was flag program, yeah, so flag program name, you can literally extract it from here. So, and essentially we can do usage, the program name, I'm going to put it like that, the program name, and this is options, like so. So, and after that we want to print the options. Let's put it like this. So it's going to be a new line, and if I remember correctly, there was something like print, yeah, print options, and you can specify where exactly you want to print the options as std error. There you go. So we're going to print the usage, and after that, I suppose, since we didn't manage to parse anything, there will be some sort of an error. So there is a function to print an error afterwards. So it's going to be std error like this. I'm going to return 1. There you go. Cool. That's basically it, right? So that's basically it. So let's implement help, right? If help was set, we're going to just print the usage and exit with 0. Right, so now we need to implement the tool itself, BP again, and let's just try to rebuild the whole thing. Did I not save nope.c? Okay, so I'm going to try to do nope BP again. What do we have in here? Okay, so as you can see, it failed at this specific place because it's not implemented yet. So let's actually do something like help. And as you can see, it actually prints all of the options that we defined in the main. So we can add more different things in here in the future. We don't really need to add more, but we can. Right, so for example, I can add an integer parameter, which is called something like x. It's gonna have a name x, and initial value is 69, and this is gonna be a value of x. And then we can add y, for instance, right? So I'm going to y for 20, value of y, and that's it, right? So that is literally it. I can now print help in the wrong folder, of course. And as you can see, it was automatically added, and so that's basically what this library is all about. So it's pretty simple, actually, right? So Go literally does it like this. Go literally does it like this. So check out this library in the description if you like it. This is not what I wanted to put in the description, actually, not the Go version. I wanted to put in the description my C version. Right, so I don't know why I put this shit in here. Who cares about Go? Who cares about Go? We're not TypeScript developers. I'm sorry. Go is a good language. I actually use Go in several of my projects. Don't worry about it. It's not about the language. People, software development is not about the language. Anyway, I talked about it way too much. So here it is. So now what we need to do, we need to load the pairs from the file. So let's load the pairs from the file. So here we provide the BP path. So now we have to provide the dynamic array of pairs. Let's allocate it somewhere on the stack. So it's pairs, and it's going to be 0 initialized, of course. And also we have to provide the temporary pointer to the temporary string builder, right? So essentially, it's not going to return anything through that string builder, but it's going to use it for temporary storage, right? It's going to load data of the file data into that string builder, so then it can parse it and verify and so on and so forth, right? So, and to free this function from managing memory on its own, we actually ask the user of this function to pass like a temporary string builder. So after this function, you can actually clean that string builder up and do whatever you want with it, right? But what's cool is that this function is going to pre-allocate a little bit of memory within the string builder. So if you're gonna reuse it, it's going to be faster, right? Because there's already pre-allocated memory in that string builder. So that's basically the idea behind all of that. And obviously, while you're loading this entire thing, it may fail, and if it fails, we're just going to return like 1, a non-zero exit code. So let's actually say something like loaded ZU pairs from S, and ZU is basically the amount of pairs we have in here, and then the file path. All right, so let's actually give it a try. So this is just a help, nothing particularly special. And so let's provide BPE, and BPE is going to be Discord BPE. Look at that. Loaded 520,304 pairs from discord.log.bpe. So we successfully loaded the pairs. So now let's actually think how we're going to generate random text out of this implicit grammar. We can start with some sort of a random token. Right, so essentially the index of the pair is the ID of the token. So what we can do, we can pick a random number from 0 to 520, 304 and call it the initial token. So that's basically what we can do. We can call it an initial token. So it shouldn't be that difficult. So this is the token. I take a random value, right, and I sort of like clamp it, not really clamp it, but mod it in pairs.count, and that gives me the token. So now we can print that specific token. We can print its number, but it's not particularly interesting in my opinion. Right, let's fucking go. So unused variable, I forgot to actually put it in here. Thank you, compiler. And yeah, so here's the random number, not that interesting. And it's, by the way, the same number because we do not set a different seed every time we start the program. So let's actually seed the random number generator with the current time. I think I have to put 0 in here. And it complains that we don't have time included, even though it managed to find it. It's just a warning. Right, so C allows you to use functions that are not declared, but if the linker finds them, it will actually use them. But it's kind of not a good practice, right? So implicit function declaration is kind of a deprecated thing in the latest version of C, but I mean, who cares? And as you can see now, it's a different token every time, but it's not really that interesting to look at the number of the token. It will be kind of interesting to look at the text of the token. So as far as I know, I do have some function that will enable me rendering the token, the text of the token, so let's quickly do that. So it accepts the table of the pairs and the token itself, and also the string builder within which is going to render this entire thing. Luckily, we already have string builder, right? It doesn't contain anything useful because, again, it's just like a temporary thing for the load pairs. So before trying to render this thing, we should probably clean it up, right? So something like this, and we're going to pass this entire thing in here. So it's going to render the text of the token into the string builder, but it's not going to be null terminated. So we have to null terminate it ourselves. So I think we have to do something like append null SB, and then after that we should be able to actually print the text of that specific token. So let's take items of the string builder and let's go, brother. That's a really funny token. So this is something that people on our Discord server actually talk. Switch will, almost instant. Forum ADelang. We talked about ADA apparently at some point. A couple of new lines. An interesting idea. We talk about interesting ideas on our Discord server quite often, right? So that's the token that represents that. So just because the token exists, it means that this particular sequence of characters occurs a lot. Right, so as you can see, we're discussing a lot of interesting ideas. Right, really proud of our community, really proud of it. But anyway, so the question is like, how can you find the next token after that? All right, so what's going to be the next token? As already said, it is kind of implicitly encoded within the table, right? So we probably need to find the pair where our token that we just picked is the left one. And as soon as we find that it is the left one, we kind of know possibilities of going to the next token. So what's funny, we can find actually several of such pairs, right? So let's go ahead and do that. So it shouldn't be that difficult in my opinion, it shouldn't be that difficult. So let's iterate through all of the pairs as usual. So just iterating through all of the pairs, count, ++i. So, and then if pairs items I left is equal to our current token. So that means we found it. So let's go ahead and just print whatever we found in here. Maybe we should collect them, because this is going to be sort of like this process where we, you know, have a current token. Let's find all of the options to go next, then pick a random option and set that random option as the next one and repeat the process and keep generating the text. So that's basically going to be the idea. So because of that, we need to have a dynamic array of tokens, right, of potential next tokens. So as far as I know, in bp.h, we do have, yeah, so here is the dynamic array of tokens. So let's introduce something like next, and it's going to be obviously null terminated, right? If we found this entire thing, we're going to di append next this entire thing but right. So that's what we're doing here. All right, and then let's actually print all of the next things that we found. All of the next things that we found. So it's going to be count like this. And maybe I'm going to actually separate all of this stuff with some sort of a line so we see that it's not part of the tokens. And in here, let's actually do the same thing. All right, so we're going to try to render the token as well. I think it's a good idea. Next, items I, we rendered in SB, so we clean SB, and so on and so forth. Let's also maybe we don't have to indent it, right? So we have a bar in here that indicates. Okay, so for this specific token, we didn't find anything. For this kind of situations, we can actually kind of declare it like a, you know, termination of the process. Okay, so there's not that many next ones, actually none. Okay, so sometimes a next one is found, sometimes the next one is found, and it actually makes sense, right? So we have this URL lin, and one of the possible you know, options that you can go next is us. And by the way, the code is incorrect in here. The code is incorrect in here. I should actually use the code of this thing, right? So that makes more sense. I'm crying. Say, high voltage, I'm crying. Full add, name 4. So, okay, it doesn't, I kind of expected that, right? So the next token is rarely found. The next token is rarely found, and I did in fact anticipated that. Particles per bomb. Okay, so the next token kind of makes sense. So let's actually see if we can find more. Okay, with, oh shit. So, okay, the next one after it does is. That's very unexpected one, but okay. It does have, it does not, it does sound, it does the, it does have a, it does seem, it does. Okay, so some of them make sense. Is doesn't make sense. It's probably we have a lot of people who don't know English grammar, myself included. So it does make sense. So as you can see, just the tokenizer already kind of implicitly contains information about the grammar of the language that we're speaking in. Isn't it cool? This is kind of cool. It does, and then an entire Discord emote feels okay, man. So quite often in our chat, people would say it does and then feels okay, man, which makes sense, right? And it is reflected within. This is fucking cool. Honestly, it does kind of suck. It does some things. And we're not building an LLM, by the way. We're not building LLM. We're just like looking at the tokenizer as a result of the tokenization, and already kind of makes sense. That's kind of cool. So, okay, but it doesn't occur very often, as you can see. So quite often we just like have nothing. Sometimes it's a jackpot and sometimes it's nothing. And how can we continue generating the text? And here is the backup plan that I had at the back of my head. So each individual token is actually pair of tokens, right? So when we're currently holding a token and we're trying to figure out what's going to be the next token, we actually hold on two tokens, the left one and the right one. So, and the continuation for the whole token will make sense also for the continuation of the right token, because the right token is basically like a narrowed version of the whole token. So if we couldn't find the continuation for the whole token, we can try to find continuation for the right part of that token. And if we couldn't find continuation for that one, we can narrow down even more because it's actually recursive. All of the tokens are recursive because of the nature of the process that we're building them with. So, and essentially, if we narrow it down to a single character, that means, well, we have no continuations and we must stop at that point. Right, and that, I think, will maximize our chances of finding continuation, right? So you can't find for the whole thing. Maybe that never occurred. Okay, so, but maybe some of the tokens kind of overlap, and you can sort of like exploit that overlap to continue this entire thing. So let's give it a try. It's actually kind of interesting. All right, so since we are, okay, so we're collecting all of the nexts in here. We're collecting all of the nexts in here. We should do that sort of in a loop, right? So let's actually put a loop in here, and I'm not sure about the condition, the end condition of this loop, so I'm gonna actually make it an infinite loop. So in a plan to reuse the dynamic array, it's kind of dangerous to do this kind of like dynamic array allocation in a loop because you basically leak in memory. So I think I'm gonna allocate it somewhere here, right? So as you can see, we have all of these things pre-allocated in here. And every time I need to fill up this array, I'm gonna be cleaning it up, right? So I'm gonna set count to 0, and then I'm gonna append things in here. Right, after we appended all of these things in here, if next count is greater than 0, right? If it is greater than 0, we can safely break out of that because we found something. But if we didn't find something, and this is where it becomes really interesting, we have to narrow down the token. So here is our token. We take its left and right part, actually only right, and I basically are reassigning it back. So as you can see, I'm reassigning it back, and because of the loop, it's going to try to do the same process again. But we have to be a little bit careful. So token may actually reach sort of its termination state, right, when it's just basically a single character. So usually that means that the token is less than 256. As soon as the token is less than 256, it means it's a single character, and within the single character you didn't find continuation. Well, you should probably stop at this point. Right, so in here I think we could basically quit as well. So maybe we should print something. Well, yeah, so we can say something like this, right? So break in both of these conditions. Otherwise, just keep trying. Okay, so let's give it a try now. So maybe that will work. Let's see. Okay, so that instantly gives us something. See that is. See that the. See that was. Okay, so that kind of makes sense. See that makes sense. All right. So you notice how it uses makes with the s after that, and that is correct, right? So it doesn't use make without the s. It's grammatically correct. It derived all of that information from the text. So let's actually try to do that. Okay, so it found something, and yeah, it finds something on every refresh. Right, so narrowing down the tokens actually increases the probability of finding something. Right, so that means we can continue generating the text. Yeah, so now it finds a continuation on each thing. somebody was spamming Pepe Happy, and continuation for spamming Pepe Happy is Pepe Happy. So this kind of thing will actually loop. I think we found a loop in here. If I continue, it will probably loop. It's kind of funny. 50 years ago? Question Sodin sus. It is kind of sus. 50 years ago, it's Sodin sus. It's kind of interesting. Bastard this. Okay, man, this is fun. Realize that the only, and there's they realize that regime knows best. Realize that the regime knows best. You have to realize that these two are two separate tokens. Just look at that. This is fucking funny. Regime knows best. That means that this combination of characters occurs very often within the text, And this combination of characters occurs very often within the text, and they quite often occur together. People quite often ask me why I'm so authoritarian. Well, I mean, anyways, that's kind of funny. So there's also fucking, of course. Of course. Okay, let's actually try to loop this entire process, I suppose. Right, so essentially, this is sort of like an inner loop within which we're narrowing the tokens, right? Within which we're narrowing tokens. And there's also outer loop where we render the text and then we need to pick the next token in here somehow. So let's actually render the tokens just like the text, but maybe split them with a bar so we can see the borders of the tokens, right? So, and this is going to be sort of like an outer loop, right? So this is an outer loop, like so. Okay, and in here, instead of printing the next, we need to basically pick the next one, right? We can pick the next one. If we can have a situation when there is no next one, and in that case we have to literally stop, right? So if so if within the narrowing we found something, we break out of this loop. If the token is less than 255, we break out of this loop, and at this point, if we break out because of this condition might be false. So that means I have to check something like this in here. So if count is greater than 0, we have to break out of this loop as well. Right, so I think it kind of makes sense. But if we still have something in here, we have to pick a random value out of that, right? And then we have to pick that element in here, and we have to reassign it back to the token. And there you go, we actually found the next token, and that next token is going to be rendered in here. All right, so we rendered the token, then we cleaned up the next, try to find the next. If next is greater than 0, okay, we found it, we're going to continue. If we didn't find it, we check if we have to stop. And then we narrow it to the right. So maybe it makes sense to limit the amount of tokens that we can generate in here, right? So we can do something like generate like 10 of them, right? So because I'm afraid, so we saw a loop in there, right, with people happy. So I'm afraid that it can actually go into the loop and just like infinitely generate. So let's actually limit the amount of text that we're going to be generating. Segmentation fault, nice. I'm super happy about that. Cool. All right. So we found something weird. Amen as possible to build code, Pepega. Okay, I'm gonna do begin. Well, I mean, this sentence kind of makes sense. And again, we are not building a language model. We're just looking at the tokenizer of the language model. We're just extracting information out of just the tokenizer, just the implicit grammar that we derived from the text, right? So let's actually generate more. So G9, and yet I'm more specific parts of the code. Okay, so can we generate anything more? I have no idea what the fuck it is. It's garbage. It's literal garbage. So let's try to maybe let it generate like 100 of these things. Okay. So it's cool. L, it's basically Discord emote, a popular Discord emote that we have. This has been my best shot. Our program in C99 potato? I see. I'm trying too hard. From China. That looks like Markov chains. Right, that looks like a Markov chains, right? So it's just like old style, chatbots, which basically try to predict the next word based on the previous word, right? Using statistics and stuff like that. And that is basically it. So Markov chains, Google up Markov chains actually. Markov chains, it's actually very interesting. So it's a stochastic, it's a modeling of stochastic processes, and it was quite often used in chatbots. Right, and then kind of when the large language models came in, large language models are basically that, but on steroids, like using actual advanced like neural networks and transformers and stuff like that. But this one was actually super simple. You basically collect statistics, how often a certain word comes after another word, and you use that to generate this kind of thing, which is basically what we did in here. It's kind of interesting that large language models within themselves contain older previous generation of language models Markov chains. Isn't that interesting? I think it's kind of interesting. So let's actually maybe remove the bars, because it's kind of difficult to read with the bars. So what do we have in here? So here it looks like text. Tenor.com view social credit score maxing. Is that a real URL, or is it confabulated, that URL? I'm actually wondering. No, it just confabulated URL. It's capable of confabulating. Just the tokenizer of an LLM is capable of confabulating shit. So it's kind of amazing, honestly. So do not need to rest from the little to no available. I wonder how many people based on their name. Okay, so it's kind of cool. It's basically like Markov chains. I wonder if you let it loose. So what if we do not limit the the generation process? I wonder if it's gonna go into some sort of a loop. Oh yeah, it went into loop. Look at that. Okay, so it hit the loop, and this is the loop basically. All right, so yeah, you have to be careful. You have to actually limit the process of generation. It can go forever. But it, like, the text kind of makes sense, right? So it just looks like a text. This isn't natural, and he will be in it too. You can, or people just go, well, I mean, when you try to read it, it doesn't make any sense. So why I was looking into that, right? So why I was looking into that, I wanted to replace our current Markov chain generation, right? So we do have this kind of thing, right? So let's actually see. It generates also different languages and stuff like that, right? Because it's based on the log. But the idea of this Markov chain is actually stupider than whatever we have in here. It's essentially collecting statistics of how frequently a certain character comes after 8 characters, right? So it sort of has like a context window of 8 characters. This one, since the tokens have varying length, it has a varying length context window, so to speak. But unfortunately, the disadvantage of this approach is that it takes too long to create the BP table. To create this 4 megabytes table, it took me like 1 or 2 hours compressing this text. So, but this model, even though, well, I mean, it produces the same quality of the text, but this model trains continuously, right? So essentially somebody sends a message, I collect the statistics of how often certain character comes out of 8 other characters and just update the database on the fly. So with this one, I can't really update anything on the fly, so I have to kind of schedule a job that takes the log and compresses it and uses the compression table as the current model and stuff like that. So it's more difficult organizationally, logistically, and stuff like that. So this one is much easier. Unless we dramatically speed up the algorithm. We already speed up the algorithm a little bit using a bunch of tricks, but I didn't even go hard on the optimization. So maybe we'll be able to speed the entire process up at some point. We'll see. I have a couple of ideas, but those ideas are for another time. So that's everything I wanted to check today. Thanks everyone who's watching right now. I really appreciate that. After this session, I'm going to actually finally publish the source code of this entire tool suite. Have a good one, and I see you all on the next recreation programming session with Mr. Azuzin. I love you all. Mwah.